In this video, I'm going to demonstrate some of the capabilities of the quantum computational chemistry software Gaussian that are particularly relevant to determining the interaction potentials, the bonded interaction potentials that one needs to perform atomistic molecular dynamics simulations. So I'll begin by launching gview, the visual interface to the program Gaussian. So gview has a builder for building molecules, and we're looking right now at the window in which you choose the fragment that you're going to insert as a molecule. The fragment is controlled by the selection over here, which gives you access to the periodic table, and also here, which gives you access to a wide range of fragments that you can insert. I'm going to build 2-butene, and so I need to insert carbons. First, I'm going to build the double bond portion in the center, so I'll choose this moiety to insert, and then I switch to this window, click once to insert that moiety, click on the unfinished bond to insert a second copy. Now I will go back and change the kind of carbon that I'm inserting to tetrahedral, and I will attach those as end groups to the molecule. Now I can quickly clean up this structure, which already looks quite nice and regular, by pressing this little whisk broom symbol, which does a little quick molecular dynamics optimization of this geometry. I want to optimize this geometry further using quantum chemistry calculations rather than just this quick molecular mechanics, and for that purpose I set up a calculation. So I use the menu Calculate underneath Gaussian calculation setup, which brings up a large multi-pane dialog box in which you choose first the kind of job that you want to do. For example, simply compute the energy of the configuration of atoms that you have prepared. That's not what we want. We want an optimization. Then the computational method, and again there are many choices here, and this video is not intended to describe the different kinds of choices to be made here. But for our purposes, what we want is a density functional theory calculation, and then we choose from among a whole set of density functionals that many people have worked out as increasingly good approximations to the behavior of real electrons. So B3-lip is a perfectly acceptable choice. And then we choose a basis set, which is roughly speaking how many Gaussian-shaped functions are being used to represent the wave function. The name of the program, Gaussian, takes its name from this sort of a basis set for those wave functions. Here we're going to choose 631G as a small but reasonable basis set for this calculation. We can give this job a title, and I'll call it 2-butene optimization. And another thing I want to do here, not absolutely everything that Gaussian can do is available in these menu panels, and for any additional keywords one types them in down here, and of course one has to know what to type. I am interested here in a particular way of trying to estimate the charge on each atom by what's called electrostatic fitting, that is, determining the charge on each atom taken as a point, which does the best job of reproducing the Coulomb potential in the near vicinity of the molecule, someplace nearby where other molecules could conceivably get to, basically at the surface of the space-filling model of that molecule. So I put this additional keyword in, and you'll see what effect that has a little later. So now we're ready to submit this job to the computational engine, and when we submit it, we'll be prompted to save a Gaussian input file, which we do here. So I'll call this 2butene.com. That's the standard name for the input file is com. And so I'll save that. And then it asks me if it's okay to submit that to Gaussian. We say yes. And then underneath the Calculate tab, there is a list of the current jobs that are running, and we can see this job is running here. So in a few minutes, this job will finish, and we'll look at the output. So now the job has finished, and we have this message here asking us, do we want to open the result file? Check is a checkpoint file, log is a log file, and there's some subtle distinctions between exactly what's in them. The log file will do for our purposes. So we open that. And we get a new picture of the molecule as it has been optimized, which looks almost the same as it did before in terms of the geometry. But now we have access to results. For example, a summary of the results includes the kind of calculation that was done, and most importantly, the formation energy in atomic units, that is in Hartrees, for assembling this molecule out of its component isolated electrons and nucleons. And it tells us the dipole moment, which this molecule doesn't have one, so it's very small. Also under the results here are the charge distributions that we calculated by the electrostatic fitting. And if we want to see those numbers on the molecule, then we can go over here and click Show Numbers, and it will superimpose on each atom in the molecule the calculated charge. These charges are a certain kind of approximation to the electrostatic charge that's associated with each atom in this molecule, and you can see these are sensible in the following sense. The protons are a bit positive, as they tend to be because the carbons tend to pull electron away from the proton, and the carbons are correspondingly negative, more or less by the amount of the charge that they pulled off of the hydrogen that they're bonded to. And the sum total of all of the charges on this molecule are neutral, since the molecule is neutral. So now we're going to turn to the problem of scanning the energy as a function of some angle or some bond length on the molecule. And this can be done in two ways. We can either scan, for example, this central bond length not touching any of the other angles or lengths in the molecule, and this is called a rigid scan. We think of just pulling these two carbons apart with everything else left the same. Or we might imagine doing a rigid scan of this angle here involving these three carbons. Let me turn the labels on with View Labels so I can speak of these with numbers. So the 1,3 bond, I could pull that apart and leave everything else the same, or I could look at the 5,1,3 angle and leave everything else the same, all the other angles, all the other lengths. Or I might explore the dihedral angle 5,1,3,4, that is spinning about this bond one half of the molecule with respect to the other half. But in that case, I might like to move the other pieces where they would like to go. In other words, I might do a relaxed scan rather than a rigid scan, where I rotate around this dihedral but otherwise optimize the molecule. So those are the two kinds of scans, rigid and relaxed. So we're going to set up to do a relaxed scan first of this dihedral angle, the 5,1,3,9 angle. And because this is a double bond, that dihedral angle is quite stiff. The molecule cannot easily be rotated around this angle by more than a few degrees, as we'll see. So to set up to do this scan, we need to save a new COM file that we can then modify. And we're going to save it out of this log file because the log file contains the optimized geometry. So we go to the File menu, click Save. I will save this as 2butene dihedralscan.com. And I am careful here not to write the Cartesian coordinates. There's two ways of saving these COM files, and I didn't remark on it before, but the first time I saved it without writing the Cartesians, and I'm going to do that again. So I'm not going to click this button. I'll show you in a little while what consequence that has. So I save that, and now I have this new COM file that I can modify. So now we modify this job, 2butene-dihedralscan.com, to do this dihedral scan that we want to do by introducing what's called a redundant coordinate. That is, by specifying that we are interested in this dihedral 5139, and that's the one we want to scan. And the redundant coordinate editor is this thing up here with the R. So I go here, I click on that R, and I have the ability to add a redundant coordinate. So I click the Add, I choose the kind of coordinate we want, which is a dihedral in this case. Here are boxes that I will put the atom numbers in, and the simplest way to put those atom numbers in is to successively click on the ones that define the dihedral of interest. And then I want to scan this coordinate, and I'm going to vary it by, say, plus or minus 5 degrees around the value that it currently has, and I will accomplish that by taking 10 steps of 1 degree. And because I want to vary around the value that it currently has, I'm going to want to adjust that value before I perform the scan. So to measure, or indeed adjust the value, these icons over here are how you measure bonds, angles, and dihedrals and so forth. And so we're going to measure and modify. So we're going to modify the dihedral, and we choose which dihedral to modify, again, by clicking on the atoms that define it. And then up comes a little panel telling us the current value, which is basically minus 180. And if we vary it, then we're being asked how to vary the atoms that it's attached to on either side, and rotate groups, you'll see, will rotate the whole thing. So if I slide this slider around, then we should see the molecule rotate live, okay, around that point. We only want to rotate it by maybe 5 degrees. So from minus 180 to 185, we'll rotate it by 5 degrees, and then if I take 10 steps of 1 degree, I'll get to minus 175, and therefore have looked on both sides of this trans configuration. So now if I take the molecule and swing it around and look down the bore of it, you'll see that it's not quite trans anymore. Okay. So if we look at the Calculate panel, we should find that the job has been already set up to be a relaxed redundant coordinate scan with the same DFT method as before, and we might change the title here just to leave a little note about what we did. And I'm no longer interested in the electrostatic charges, so I'll take those keywords out. And now I can submit this job, which will prompt me to save this file. I have already saved it, and the changes I made will overwrite the copy that is there. So if I save that, it will warn me that I am overwriting, and I'm going to do that. And then it will ask me, do I want to run the job? And I do. And so the job is launched. And again, we'll need to wait a while in order for the job to finish. This will take roughly 10 times as long as the job we did before because, of course, it's doing 10 different configurations as the dihedral angle is advanced, and each of those is optimizing the geometry. So the job is finished now, and to see the results of the scan, we're going to look again at the log file. And now we see that the log file has not just one picture, but a whole list of them, and we can advance through them by clicking the up arrow and the down arrow. And it's not a very big change because we didn't make a very big angular change, but as I'm clicking through these, it's actually slightly rotating the molecule from one frame to the next. That might be more evident if I look at it on end. And you can see that ever so slightly the angle is being rotated around the trans minimum. So to see the results that we're interested in, what we want to know is the energy as a function of that angle. And so we go to the results, scan, and we see a plot now of the total formation energy of the system as a function of that scan coordinate. And we can see that indeed 180 degrees is the minimum energy, and that there is a certain increase, a quadratic increase of the energy as we deviate from that in either direction. So that's nice, this plot, but we might want to save these values so that we could, for example, extract this curvature and therefore determine the stiffness of the spring, so to speak, that is keeping that dihedral near 180. So to extract those numbers, we command or right-click on the graph itself to pull up this panel here, which allows us to save the data. And we can save it as a text file, which we'll call dihedral.txt. We can also save the graph itself in various forms, including a scalable vector graphic or a PNG. So I'll save a PNG here just to show how that works. So now we're going to do a rigid scan, let's say, of the central bond length. And to do that, I'll open again the log file from the original optimization and save this as a new COM file that I will then edit, and I'll call this bond scan. Again, not saving it with Cartesians being written. So now we're going to go over into this other terminal window and look at the file that we just made, this COM file. What's in it? So here's the file. Right now, it's, first of all, you see it's human readable. So this first line is telling what the name of the check file is, that it writes a check file every once in a while as it's going along. The second line is basically the command to Gaussian that is being executed, which is an optimization job using a certain density functional and basis set. This pop equals ESP was meant to be taken out, and I'm going to take it out now. And geometry equals connectivity is describing this mess of numbers down here, which is actually a description of where all the atoms are, as I'll describe in a minute. So now I'm going to change this title, that's the title right there, to bond scan. So what we're looking at here is a specification of this molecule in a certain format called a Z-matrix. And it's helpful if I turn the labels back on so that we can look at the atom numbers while we look at the Z-matrix. So first it tells the total charge and the spin state. Charge 0, spin singlet, that's the 0 and the 1. And then it starts listing the atoms in the order of these numbers here, the order that they got added in a certain sense. So here's carbon number 1, that's the first atom. There's the hydrogen, that's the second atom. And you see it's bonded to atom number 1 with a bond length B1. And then the next carbon, that's atom number 3, okay, is bonded to 1 with a bond length B2, and then it has an angle 3, 1, 2 with defined by that carbon I just added, this one, and the hydrogen that was there before, with an angle A1. The next hydrogen is atom 4, okay, this one here, bonded directly to 3 with a bond length of 3, an angle 4, 3, 1 with an angle A2, and then a dihedral 4, 3, 1, 2 with a dihedral D1, and so forth. Okay, now you can see that there'd be many different ways of constructing a Z matrix, and so Gaussian has constructed it basically in the order in which the atoms were added. You note that the methyl groups I put on at the end are 5, 6, 7, 8, and 9, 10, 11, 12. Those atoms were the last ones added. So these values of these bond lengths, angles, and dihedrals have all been listed below here with their numerical values. That is what I accomplished by, at the very beginning when I built this thing, not writing Cartesians. I get all these nice variable names and all of their values down here. And now we're going to put that to work as follows. We want to scan this bond between 1 and 3, which, as I said, this is the first atom up here, first, second, third, and the bond that connects that to atom number 1 is called B2, and that's this bond right here with a length of 1.34 angstroms. We can just validate that by going in here and measuring that with this inquiring measuring stick. If I click on that atom and that atom, I'll see that's 1.34 angstroms. So that's the one we're talking about. So right now it has a constant value, and we're going to go down and edit this file and make that value step from 1.3 to 1.4 in 10 steps of 1/100th of an angstrom each. So I'll change the rest of the line to have 10 steps of 1/100th of an angstrom, and that will get me from 1.3 to 1.4. And then I just go back up there, and where the word opt appears, I change it to scan. And so I've edited the COM file outside of Gaussian in order to do something that can't be done within gview, which is to prepare this rigid scan COM file. It's rigid, meaning the only thing that will change when the stepping happens is the value of B2. None of the other bond lengths, none of the other angles, none of the other dihedral angles will be changed, only that bond. And so these scans are appropriate when you want to look at how the energy changes when only 1 degree of freedom is changing. These are very fast because no optimization is being done on any step, only a single point energy calculation, that is a calculation of the energy with the atoms in a precise arrangement. So I will save and quit that file. And now to launch the job, okay, I don't go back into gview to launch this. The simplest way to launch it is just by invoking the program Gaussian from the command line. It's called G09, Gaussian 2009. And I give the name of the COM file that I want it to compute. And then I'm going to launch this job in the background, just so I'll have access to this command line. So with an ampersand, the job is launched in the background. If I want to see that the job is there, you see a job number was given, 37677. If I type PS process, okay, I will see that that process is running. And very soon, because this is quite a simple job actually, that process will complete. And it won't give me any explicit message that that has happened, but if I wait a little while and then hit a carriage return, well, it's not done yet, then the job will send me a little message saying it's done. In the interim, I could do other work at this terminal window, and the job would be running, as I say, in the background. If I were to log out or exit this terminal window, the job will be killed. So this is not an appropriate way to run jobs that take hours and hours, but it is an appropriate way to run a job that takes, some minutes. So now the job is finished. As you can see, I hit return one more time and got this message telling me that the job is done. And now I'm going to go back into Gauss view and look at the results from the rigid scan. So I will open the log file from the bond scan. And once again, I get one of these molecule windows with a number of frames. And if I click on this and advance through the frames, it should make the bond ever so slightly longer. And if I want to look at the results, numerical results from that, then I go to the results and then scan, and then I see the total energy as a function of that bond length, and indeed the minimum is at the 1.34 something or other length that the optimization gave. And if I want to save these results, then I would do as I did before and right-click the graph to save the data as bond.txt. And if I want to save the graph itself, I can do that by exporting the graph as a PNG bond.png. So the curvature of this energy versus length is telling me about the spring constant that controls the length of that bond. Now if I look inside the files that I've made, those bond.txt and dihedral.txt, I see that they just consist of XY data, so to speak, where X is the scan coordinate, here the bond length in angstroms, and Y is the total energy of the system in Hartrees. And it's only changing out here in the third and fourth decimal place. Most of the formation energy of this molecule is not affected when you stretch that bond, but the curvature around the minimum nonetheless is representative of the spring constant for that particular deformation.